Hi, my name is Nicholas Balk, and for my graduate presentation for Power System Fundamentals, I'll be speaking about electric vehicle integration into the grid. So why do we need electric vehicles? Well, traditional gas-powered vehicles that most people drive produce many carbon emissions, which are known collectively as greenhouse gases because they're responsible for the rising temperatures on Earth's surface, much like a greenhouse. Out of any industry in America, the one that produces the most greenhouse gases is the transportation industry, with about 28% of the US's greenhouse gases. Of that 28%, 80% of those are from cars and trucks. Electric vehicles, on the other hand, produce zero tailpipe emissions. The only emissions that they do produce are on the generation side. And what this does is it shifts the environmental focus from transportation to energy production, where we already have solutions, and solar is actually the largest contributor to new electrical generation capacity in the US. We also have other clean solutions such as nuclear and other renewables. So how do electric vehicles charge? So there's three types. Level 1 is just a wall outlet, and it's the slowest form of charging. It's typically provided with the new electric vehicle, and you can just plug it into any outlet in your home or garage. It adds about 2 to 4 miles of range per hour, or 1.3 to 2.4 kilowatts. It's good for if you're not driving a lot today, just to work and back, getting groceries, etc. Level 2 is a 240 volt outlet. It's faster charging, and it typically needs to be installed in your home. It's 6 to 8 times faster than level 1. And the 24 amp charges at 6 kilowatts, but it can go up to 80 amps or 19 kilowatts, which is significantly faster than level 1. Lastly, we have DC fast charging. This is the fastest charging mode. It's a high voltage with extra pin connections, and each company has its own version. For example, the Tesla Supercharger. These can charge 50 to 350 kilowatts. However, it's important to note that the car charging capacity may not be able to handle certain DC fast charges. In terms of the cost benefit to the consumer, although there is a higher upfront price, you will save money on your mileage. So it costs about 5 cents per mile or $56 per month to charge on average, compared to 13 cents per mile or $145 per month to gas up your car. And electric vehicle batteries have a wide variety in capacities. Gas is typically higher. For example, the highest range you can get on an electric vehicle right now is 315 miles from the Tesla Model 3 Performance, and it takes longer to charge than it does to gas up your car. So that is a major convenience factor that gas has over electric vehicles. Now, to charge all of these electric vehicles, there's going to be some major transitions on the electric grid, which can severely affect the existing power systems. So in the most extreme case, the average electric car uses about 35 kilowatt hours per 100 miles, and the average US annual mileage is 13,500 miles. This gives us about 4,600 kilowatt hours per driver per year. Now, like I said, in the most extreme case, if every driver in the USA went and bought an electric vehicle tomorrow, it would add 1 trillion kilowatt hours per year to the grid. This is a quarter of our total electrical consumption of 4 trillion kilowatt hours in a year. Thus, we would be increasing our consumption by 25%, which is, at the moment, completely infeasible. In a more realistic case, the adoption of electric vehicles is expected to add about 100 to 185 billion kilowatt hours, or 2.5 to 4.6% of our grid's capacity by 2030. Now, electrical generation capacity has grown by about 18 gigawatts per year on average for the past 20 years. And the generation capacity typically keeps pace with the increase in consumption, but electric vehicles are going to place a massive strain on this. And it's not just about how much capacity you need to add, but when and where. You can see from the graphs on the right that the electrical consumption on a daily basis is not a smooth or uniform curve at all. It actually peaks in the afternoon, and in the winter it has 2 peaks, and the difference there is just due to different heating and cooling cycles. But typically, electrical consumption will peak in the afternoon when people get home from work. They're also going to plug in their cars and charge them when they get home from work. Thus, this will just increase the peak load even more than it already is. So there's a major problem with overloading the grid at specific times. The electrical vehicle distribution is also not uniform at all. The West Coast states such as California, Washington, and Oregon lead the way in electric vehicle purchases, and other states not so much. Thus, with all these factors combined, there's a major challenge in creating generation capacity to be able to match the peak hours as these electrical vehicles become more prevalent. In the next few slides, I'll discuss 3 different systems which have all been demonstrated or piloted in some capacity somewhere in the United States. So first up, we have time of use charging. Time of use charging is essentially giving a financial incentive to charge at specific times when the demand is lower. Pacific Gas and Electric in California has already offered such incentives, and participants actually saw savings of up to 15 to 20% on their utility bill. It also helped to reduce overall grid stress, and you can see the image on the right is a graphic by Unitil, which is a utility company in the northeastern United States. It shows how their pricing changes depending on the peak times. Problem with this is that it can actually create overload at the conclusion of these time of use periods. So, for example, one study actually showed that the new peaks that were created by a time of use after midnight charging program caused the older distribution transformers to fail more often. To solve the issue of peak loads at the conclusion of time of use periods, an alternative solution could be managed charging infrastructure. So vehicles are parked about 96% of the time, and in that case they're underutilized assets. Thus, they can be charged at more strategic times to avoid overloading the grid. That's what managed charging aims to do, is to smooth out that peak load. As you can see from the image on the right, it can take the huge peak that's on the right there and smooth it out over the entire day, which makes it much more manageable and also saves you a lot of money in terms of power system investment and operating costs. Baltimore Gas and Electric has already pioneered a program where participants chose to allow the utility company to limit their electric vehicle charging to specific times, and they saw 30% participation when they gave financial incentives. The main problem is that there are ethical concerns, such as privacy. These programs have concerns related to collecting data on consumers, such as when they charge and how often. The last solution we'll discuss here is vehicle-to-grid technology. So this technology is essentially letting your vehicle supply the grid while it's not being used. You charge it during the off-peak hours, and then it can actually act as a sort of battery during the peak hours. And a partnership between Revel, Fermata Energy, and 9 Energy in New York City has shown that the potential is to turn electric vehicles into essentially decentralized energy assets is actually well underway. However, it'll require massive infrastructure changes because you'll need bidirectional charging for a lot of these different places. In terms of relevance to what we learn in 546, we've talked a lot about distributed power systems, where each generator is essentially expected to produce for its own area, but if it becomes overloaded, there's other nearby generators that can pick up the slack. Vehicle-to-grid essentially is doing this on a much more decentralized way, and managed charging systems can use forecasting to predict and mitigate future peak loads. Recall the lecture given to us by Dr. Mohammed Shahidapur, where he showed how microgrids can help to reduce peak loads in a very similar way. So, to wrap it all up, electric vehicles are an inevitable transition that the US is going to take, and they're good. They solve a major environmental and health and safety problem, that is greenhouse gases and other pollutants from cars. However, the rapid adoption of electrical vehicles in the US is and will pose a massive challenge to our existing electrical grid. 3 solutions that we've discussed are time of use charging, managed charging, and vehicle-to-grid. However, they all have their own flaws. Thank you very much.